Hi ma'am, my name is Sayapurva Vedangi and today I will be presenting the AOA programming project in Java. We are given one problem statement, that is we need to find the closest pair of points. We will be given set of points in a coordinate plane. We need to identify 2 points among all those points in such a way that the distance between 2 points is the minimum. Here there are so many types of distances like Euclidean distance, Manhattan distance, etc. We need to consider Euclidean distance in this project. We were asked some additional requirements along with this efficient algorithm. Those are, we need to solve the problem statement in two different approaches. One is brute force approach and the other one is divide and conquer approach. We need to perform the runtime analysis of these two algorithms over 10 different inputs. The inputs can be of our choice and it is better to choose as large inputs as possible in order to analyze the exact time complexity for larger values of n. For each value of n, we run the code for m different arrays. The inputs for the m different arrays will be generated by a function called random number generator in Java. So basically, finally, what we are doing is we are running two different algorithms for one single problem, closest pair of points, and those algorithms are divide and conquer algorithm and brute force algorithm over 10 different inputs. And for a specific input, we are calculating it on m different arrays generated by random number generator. And for a specific value of n, the empirical time complexity is calculated by the average time complexities of all the different arrays. So, moving on to the brute force algorithm. The brute force algorithm always calculates the worst case runtime complexity. It is nothing but tracing the problem right from the starting to the end without any optimization of the code. For example, we are given set of points in a coordinate plane. The brute force algorithm could be, we calculate the distance between every point to the other point and we store the values of the distance, and if that distance is less than the previous distance, we will update the minimum distance. Here we are calculating the distance between all the points to the other points. So it will take a lot of time and it is the worst solution we have been providing for the problem. This is the brute force approach. If you read here, the brute force algorithm is a straightforward approach to solving problems by systematically checking all possible solutions and selecting the best one. In the context of the closest pair of points problem, the brute force algorithm works as follows. For each pair of points, it calculates the Euclidean distance between them by using the distance formula square root of x2 minus x1 whole square plus y2 minus y1 whole square. It keeps track of the minimum distance found so far and the corresponding pair of points. After iterating through all pair of points, it returns the pair of points with the minimum distance. Here if we consider the pseudocode, this is a pseudocode that has been explained in the class. Here if P is a list of points, then we will be having two loops. One loop runs from I to n minus 1 and the other loop runs from I plus 1 to n. Here we are calculating the distance between one point to the other points. And we assume the d minimum as infinity. If the calculated distance is less than the minimum distance, we will update the minimum distance in such a way that there are n into n minus 1 by 2 possibilities to run this entire pseudocode. So if it is n into n minus 1 by 2, the worst case complexity will be big O of n square. This is what that has been explained in the time complexity analysis. If we look into it, the brute force method operates with a time complexity of order of n square, where n represents the number of points. This complexity arises from the necessity to calculate the distance between each of the n points and the remaining n minus 1 points. Consecutively, the total number of distance calculations amount to n into n minus 1 by 2, resulting in a quadratic growth in computational effort as the number of points increases. As there are two loops, it is order of n square. And there comes the divide and conquer algorithm. In divide and conquer algorithm, we follow a specific approach in which we divide the array, we conquer it, and at last we combine it. It is a very powerful technique that is used to solve many problems in less time complexity. If we want to go deep into divide and conquer algorithm, the divide and conquer algorithm is a problem solving strategy that involves breaking down a complex problem into smaller, more manageable subproblems. In the context of the closest pair of points problem, the algorithm divides a set of points into two subsets based on their x coordinates, recursively finds the closest pair of points in each subset, and then combines the solution to determine if there exists a closest pair of points that spans both subsets. By efficiently partitioning and conquering the problem and then merging the solutions, the divide and conquer algorithm efficiently identifies the closest pair of points in a given set. This approach reduces the overall complexity of the problem by decomposing it into simpler tasks, ultimately leading to an optimal solution. If we consider the pseudocode, this is a pseudocode that has been explained in class for divide and conquer algorithm. Here, we find the closest pair by measuring all pairwise distances. Q naught star to Q1 star is the closest pair recursion for Qx and Qy. R naught star comma R1 star is the closest pair recursion for Rx and Ry. And delta is the minimum value of these two. And x star is the maximum x coordinate of a point in set Q. We will calculate recursively. We will trace the points recursively. The steps to be followed are divide, conquer, and combine. We compare all the distances and at last we'll print the minimum distance. If we come to the runtime complexity of divide and conquer, from this pseudocode we can say that the recurrence relation for this runtime complexity is T of n is equals to 2T of n by 2 plus Cn. If we observe carefully, this is in the form of a equation which can be solved through Master's theorem. And we know that the Master's theorem is T of n is equals to A into T of n by B plus f of n, where A greater than or equal to 1 and B greater than or equal to 1. From this equation, A is equals to 2 and B is equals to 2. So after solving the Master's equation from the formula, we get the f of n is equals to C of n, and the order of time complexity is order of n log n. So by observing this time complexity, we can easily say that divide and conquer algorithm is much more efficient than the brute force algorithm. This is the source code. I have implemented the code in Java. First, I wrote the code in this notepad file, and later I have executed it through my terminal. The compilation command of my terminal is javac space test1.java. The file name I kept for the Java file is test1.java. And after the compilation is done, there were 0 errors in my code and it did not return any error. Later I executed the entire code by this statement java space test1. After executing the code, these are the results I got for different values of n. The values of n I generated are 10, 70, 100, 700, 1000. I mean, I took the multiples of 7 and incremented into 10 for everything and calculated the runtime complexity of brute force and divide and conquer. This is the output of my code, and if I want to show my code, uh, this is my code. Just a minute. This is the code. In this code, I have used multiple methods. If I want to explain the deep, then there is one class called point class in my code. This class represents a 2D point with x and y coordinates. It has a constructor to initialize the x and y coordinates of the point and generate random points method. And this method is used to generate a specified number of random points within the range 0 to 100 for both x and y. It uses a hash set to ensure uniqueness of points. It returns a list containing the generated points. This method calculates the Euclidean distance of the point. I'm talking about the distance method, and it uses the Euclidean formula we have discussed earlier. And there is one more method called brute force method, and this method finds the closest pair of points among all the points. It iterates through all possible pairs of points and calculates the distances. It keeps track of the minimum distance and the corresponding pair of points, and there we'll get the divide and conquer algorithm. divide and conquer method. This method finds the closest pair of points using the divide and conquer approach. If the number of points is small, it resorts to brute force. Otherwise, it recursively divides a set of points into two halves. It finds the closest pair of points in each recursively. It then combines the results by considering the minimum distance between the closest pairs in the left and right halves. It also checks for the minimum distance between points lying in the strip region, which a vertical strip of width 2 into minimum distance around the middle line. And the main method, it contains an array n list specifying different values of n number of points. It also specifies the number of iterations to calculate average time complexities. For each value of n, it generates random points and calculates the average time complexities of both brute force and divide and conquer algorithms over multiple iterations. It prints the average time complexities for each value of n. Overall, this code demonstrates two approaches, brute force and divide and conquer, for finding the closest pair of points among a set of randomly generated points, and it measures and compares their average runtime complexities for different number of points. So, and the output of the code is shown here in this terminal. Thereafter, coming again to the project report. Here, this is the these are the tables that were drawn from the output. These are the n values we have taken, and the theoretical runtime complexity for brute force is obviously n square, and we'll square these values 10 square, 7 into 10 whole square, and this is the theoretical RT. And the empirical RT is the RT that we get here in this code, the average runtime complexity of brute force algorithm. This is in seconds, and in the report we have converted it into milliseconds. And the ratio is nothing but empirical RT by theoretical RT. That means this one by this one. And the predicted RT, we have one formula. These are the values of R1, R2, R3, R4. Now the C1 is nothing but maximum of all these values. Of all these values, the maximum one is 0.00018. So therefore, while calculating predicted value of RT, we will multiply this value by theoretical RT. And this is a predicted RT results for brute force algorithm. In the same way, we'll fill the table for divide and conquer algorithm. This is the n value. This is a theoretical RT, empirical RT. Empirical RT can be formed from the code, and the ratio is this by this. And theoretical RT here we'll calculate by using n log n. And predicted RT comes from the value of C2, which is 0.02759 into theoretical RT. And while plotting graphs, I plotted the graphs in Google Collaboratory Notebook. I have attached the file of this Google Collaboratory Notebook. And here there will be three graphs. One graph is between empirical RT of brute force versus empirical RT of divide and conquer. If we observe, for small values of n, there is not much difference between these two. But for big values of n, we are observing a lot of difference. What we have observed is brute force is taking more time to calculate than the divide and conquer. For small values of n, these two, divide and conquer and brute force, they will coincide and they will run in the same way. But for very, very small values of n, what we have observed is divide and conquer is taking more time than the brute force algorithm. And the second graph is for empirical running time of brute force versus predicted runtime of brute force. For the small values, both are same. That means the predicted and the empirical values are same, but for the large values, it is going in a different way. In the similar way, this is the empirical RT of divide and conquer versus predicted RT of divide and conquer. For small values, there is not much difference, and for large values, there is a lot of difference. And the main point that is to be noted is these are for the n values which I took. If the n value varies, these graphs also vary continuously. So the final conclusion which I can draw is for large values of n, these two act differently and divide and conquer is more suitable. For small values of n, these two act in a same way, mostly brute force and divide and conquer, and for very, very small values of n, divide and conquer acts well. And this is the conclusion, and these three are the references. Thank you for this opportunity. And this is the whole project.